In this video, we're going to work example problems related to finding areas between curves using integration. So we'll be given a set of curves, two or more curves, and we want to find the area contained within those curves. So here, this red curve is y is equal to e to the x. This blue curve is y is equal to x squared minus 1. And then here's x is equal to minus 1. And then here's x is equal to 1. So we want to, and for this problem, we want to find this area. Now, sometimes we might not be given vertical lines like this. So for this problem, let's say they omitted x is equal to minus 1 and just gave us these three curves. Then what they're saying is the area contained within the curves would be, so we would use this intersection point between e to the x and x squared minus 1. So we would be finding this area. And then if they didn't give us x is equal to 1 as well, then we'd be using the intersection point on the opposite side as well. We can't see an intersection point here, but if they didn't give us x is equal to 1, then we would be able to see another intersection point. And so the integral that was developed in this section for finding these kinds of areas between curves was, so the integral from a to b of f of x minus g of x dx, where f of x is greater than or equal to g of x for all x on the interval from a to b. And so we can see that is the case here if we treat e to the x as f of x and x squared minus 1 as g of x. But more generally, if we want to look at this in complete general, the formula that was given was the integral from a to b of the absolute value of f of x minus g of x. And so this, included within this, is this, because if f of x is greater than or equal to g of x for the entire interval, then you just remove the absolute value and you get this integral here. But if, you know, the idea here is that you might have some mixture where the curves are interweaving. And so if you want to find, the idea is you want to find the total area. So you want to find this area plus this area plus this area. And what this formula does here is that the way you can look at this, one way you can look at this absolute value is that it's like a piecewise function where you take, all right, let me put this back. So we're going to find this area plus this area plus this area plus this area. If this is g of x and this is f of x, then it's like a piecewise function in that you break this up into these intervals. Like here's one interval, here's another interval, here's another interval, here's another interval. And the function is just whatever's the greater function you put first here. So for this region, it would be g of x minus f of x. Then you'd integrate from a to this point. Then in this region, it would be f of x minus g of x, and you'd integrate from this point to this point. You do 1, 2, 3, 4 separate integrals. Just alternating, just making sure for each of those integrals, you're putting whatever the greater function first in this subtraction. And so with that, you get the sum of the areas. Now, as we go through each of these problems, we don't want to just blindly use this formula. We want to analyze the problem and check that the way it's set up, the way we're approaching the problem is based on the way that this was developed. And so what I mean by that is, you know, just check, okay, do we have a function that's always greater than another function? Are we getting the limits of integration correct? The independent variable, okay, we're going to see problems where it's better to use the y-axis as the independent variable. So remember this dx here, we're for integration, we're breaking up into equal pieces the independent variable. The delta x, it's really the delta independent variable. Okay, so we just want to analyze the problem and just to, you know, make sure we understand how this integral was developed, and that, you know, every problem is going to be unique in its own way. So we want to make sure we're applying the integral correctly. All right, so let's do this first problem here. We can see that, yeah, so we're going to be we're going to have x be the independent variable. So we're going to be using dx, and we're going to be integrating from x is equal to a to x is equal to b. We're going to be breaking this up, this interval here up into equal width pieces, and then our rectangles are going to be based on these function values evaluated at the x within the interval. And we're going to do the height of the rectangles is going to be this function minus this function, which, since this is negative, it ends up being this function plus the value here, so you get this total length. If this blue curve were like here, then you do this function minus this function minus this function minus this function, and you get this length. So this works. This formula works for any scenario, assuming f of x is always greater than g of x. Not in terms of magnitude. So even here, f of x would still be greater than the blue curve, even though the blue curve is more negative. So, okay. So the limits of integration are going to be from b is equal to, so from a is equal to -1 to b is equal to 1. All right. And so we want to integrate from -1 to 1. And so this is e to the x, and this is x squared minus 1. So e to the x minus x squared minus 1 dx. That's the area. So this is equal to e to the x minus x squared plus 1 dx. Okay, so this is, let's do the integration. So we've got e to the x minus 1/3 x cubed plus x, going from -1 to 1. Okay, so this, plugging in 1, we've got e minus 1/3 plus 1, then 1 over e plus 1/3 minus 1. Okay, so e minus 1/3 plus 1 is plus 2/3. Okay, 1 over e, 1/3 minus 1 is minus 2/3. So this is e plus 2/3 minus 1 over e plus 2/3. So this is e minus 1 over e plus 4/3. That is the area between the curves. That is this area. Okay, so here they give just two curves, and they don't give an interval. Well, they don't give x is equal to, like if they just give x is equal to, that means they're giving vertical lines. And the reason is because what they're saying is just whatever's contained between these two curves, just these two curves. So we're looking from here to here, right? If they were just saying from, like here to here, then they would include x is equal to whatever this is and x is equal to whatever this is. But they're saying between these two curves in general. So they're looking for this area. Okay, and so we can see that we just need to use the general integral again for the area between two curves, where one curve is always greater than or equal to the other curve over the interval. And also, I mean, you want to analyze this to make sure that if you're going to just go plug into this formula like plug and chug, you just want to make sure that the way what you're analyzing reflects this formula, okay? And so, yes, we have one curve that's always greater than or equal to the other curve over the entire interval. What else? The dx, right? The pieces are based on, they're broken up into these equal pieces. The independent variable is x here. The function values, the f of x, it's this minus this minus this. So I'm saying this because we're going to see examples where we treat y as the independent variable, right? So it would be a similar problem, but we're treating y as the independent variable. So we have to adjust the formula a bit. And so it's important to understand what this formula means and how, if we treat this as f of x and this as g of x, and we can see what our interval is going to be from here to here, we can just do like a plug and chug into this formula, okay? But we need to, before we can set up the formula, we need to know what the endpoints are. So it looks like it's just 1 and 4, but let's see if we can verify this, get exact, like that's an estimate, right? Let's see if we can get exact answers to that. So what would we do? We would set these two functions equal to each other and solve for x. So we've got x squared minus 4x plus 4, then bring over the x is equal to 0. So x squared minus 3x plus 4 is equal to 0. Okay, so x 3, 1, or no, 4, 1. 4, 1, or wait, no. Minus 4x minus x is equal to 5. Equal to minus 5, so, okay. So now we've got, so x 4, 1 minus. So yeah, x is equal to 1 and x is equal to 4. There we go. So now we can set up the integral. We're looking to do this infinite sum of these areas going from 1 to 4, okay? And then f of x is, or no, yeah, this is f of x. This is g of x. All right, so it's going to be x minus 2 squared. Let's do that over here. X minus 2 squared is equal to x minus x squared minus 4x plus 4. Okay, so this is minus x squared minus 3x minus 4. Yeah. Okay, so there we go. So this is minus 1/3 x cubed minus 3/2 x squared minus 4x. So you take this derivative, you get minus x squared. Here you get minus 3x. Here you get minus 4x. Okay. Evaluated from 1 to 4. So minus 64 over 3. And then 16 times 3/2 is minus 24. Minus 16, okay? And then minus 1/3 minus 3/2 minus 4. Okay, so minus 64 over 3 minus 24 minus 16. Okay, then the other side is minus 1/3. Okay, minus 3/2 minus 4. So now this minus this, minus 111 over 2. Okay, let's see where this should be. So you got minus x squared. All right, went too fast here. So this is x minus x squared plus 4x minus 4. So minus x squared plus 5x minus 4. Okay, so this is plus 5x. And so this is plus here. So this is plus, and this is plus. So this is plus, and this is plus. And you've got this minus this. Why is it negative? It should not be negative. So let's see. Okay, yeah, so this would be the minus plus, okay, plus 5x would be 5/2 x squared. Okay, so in that case, 16 times 5, 80 over 2, so 40. So this is 40. Okay, and then this would be 5/2. All right, so let's start this over. So minus 64 divided by 3 plus 40 minus 16. 8/3, okay? Now, minus 1/3 plus 5/2 minus 4. So we've got this minus this, 9/2. There we go. So this area here is equal to 9/2. Okay, so we want to find the area contained between the curves 1 over x squared, and x is equal to 2. The red curve is 1 over x, the blue curve is 1 over x squared, and then here is x is equal to 2. So we're looking for this area. All right. So can we just plug into the general formula going from A to B? F of x minus g of x dx? Yes, because we've got, for the entire interval, we've got this function here is greater than or equal to this function over the entire interval. And the independent variable is the x-axis. So we're going to be subtracting the values of the function, right? So this is exactly how this formula is set up. The dx's are going to be, we're going to be breaking it up into pieces along the interval along the x-axis, and then we're subtracting the values of the function to get the height of the rectangle, right? This function minus this function gives the height of the rectangle. So we can just plug straight into this formula. Okay, so we're going from, it looks like x, let's make sure that these two functions meet at x is equal to 1. So 1 over x squared is equal to, or 1 over x is equal to minus 1 over x squared. So x squared is equal to x. X squared minus x is equal to 0. X times x minus 1 is equal to 0. So it's x is equal to 1. Not x is equal to 0 because that's outside of the domain. That's like an extraneous solution, right? You say, oh, they meet at x is equal to 0. Well, no, they don't exist at x is equal to 0. So there you go. X is equal to 1 is this point. So we want to find the definite integral from 1 to 2 of f of x minus g of x. Okay, this is it. We evaluate this. That's the area under the curve. So, okay, this is equal to x to the minus 1 minus x to the minus 2 dx. Okay, so okay, we have natural log of the absolute value of x, that's the integral of 1 over x, minus x to the minus 1 over minus 1. So plus 1 over x. Evaluate this from 1 to 2. Okay, natural log of 2 plus 1 over 2 minus natural log of 1 plus 1. So this is natural log of 2 plus 1/2. E to the 0 is 1, so this is 0. So just minus 1. So this is natural log of 2 minus 1/2. There you go. That's it. That's this area here. Really cool. Okay, let's find the area contained between these two curves. This is 12 minus x squared, the red, and the blue is x squared minus 6. Okay, and so it doesn't give us any x values, so like they're not saying contained between, x is equal to minus 1 and 1 and those two curves, which would be like this area. So what that means that they're saying that contained between just these two curves in general. So just this area. And so can we use the general formula, yes, because, okay, we will treat this as f of x. This is always greater than or equal to g of x, the g of x, which is this, over the entire interval. And the dx here, we're breaking it up, the area up into pieces, and we're going to break this up into pieces. This is the independent variable, and here the heights are the function evaluated at each x. Again, we're going to see other problems where we use y as the independent variable, so we'll have to adjust this a little bit. You just want to make sure that you understand exactly, even though they derived this formula for us in the textbook, you still want to compare your problem to the formula in terms of with your understanding of integration to make sure that you're applying it the right way. So, okay, now what is a and b? We need to set these two functions equal to each other and solve for x minus x squared. So, okay, we bring the x squared over, 2x squared minus 6 minus 12 minus 18 is equal to 0. So 2x squared minus 9 is equal to 0. So x is equal to plus or minus 3. Okay, so we want to integrate from minus 3 to 3 f of x minus g of x. So 12 minus x squared minus x squared minus 6, which is, so 12 minus x squared minus x squared plus 6. Okay. Dx. So minus 2x squared plus 18. So we can factor out a 2. Okay, now if we look at this definite integral here, if you replace x with minus x, you get the same function, right? So in this case here, f of minus x is equal to f of x. This is an even function. So based on properties of symmetry with definite integrals, we can take a 2 out, so we're left with 4, and then this goes from 0 to 3. Okay? This will make it a little bit easier to solve. So we've got 9x minus 1/3 x cubed evaluated from 0 to 3. So this is 4, and then 9 times 3 is 27, and then 3 cubed divided by 3 is 3 squared. So that's the first part, and then minus this evaluated at 0, it's just 0. So this is 18 times 4. 72. And there you go. This area, S, is 72. All right, let's find the area between these two curves over this interval. And so the red is secant squared x, and the blue is 8 cosine x. So we're trying to find the area contained between these two curves. So this area, assuming that these intersection points here are equal to minus pi over 3 and pi over 3. We need to verify that. It looks like they are. So this isn't a video talking about how to solve equations, so let's just plug this in to the calculator. So we want to solve secant x squared is equal to 8 times cosine x for x. All right, so when n is equal to 0, you got minus pi over 3 and pi over 3. Yeah. So it's these two points. It's between these 2 points, right? Because they could have given us like between minus pi over 4 and pi over 4, right? That would be a valid interval. So that would be, you know, something like this. So we want to find this area. So we need to check. We need to make sure that this is referring to these intersection points, and it is. Okay, so now can we use this general formula, the main formula that this section derived? Can we use this? Yes, because, you know, again, why am I asking, can we use this? Because, well, yeah, so obviously this is the formula they developed, and we're finding areas between curves, so let's just use the formula they developed, that the textbook derived. But we're going to be using a similar type of formula to find areas that are contained within the y-axis. And so it's always good to double check. Like, you need to understand where these formulas are coming from and double check that, okay, this infinite sum that I'm doing, is that accurate? Is that pertinent here? Do I need to change up this formula a little bit or something? You know, you want to understand what you're doing whenever you're doing an infinite sum like this. So why is this, can we just go ahead and use this formula here? Well, we can check the dx. You're breaking up the independent variable. It's not always x. Again, the independent variable we're going to use is going to be y. We're going to have the independent variable be y in upcoming problems. But here it's x, and that is the case here. We're going to be breaking up the independent variable along this interval into equal pieces, and then the height of each of those, we're going to be multiplying that width of the independent variable, that equal width, each one of those intervals, we're going to multiply to get like a height of a rectangle, and that height is going to be based on the function evaluated at an x within that interval. So like it'll be this will be f of x, and this will be g of x, right? This formula is such that f of x is always greater than or equal to g of x over the entire interval, and so that's the case. So, okay, let's just go ahead and evaluate this formula. So we're going from minus pi over 3 to pi over 3. Okay, the f of x is 8 cosine of x, and then minus secant squared of x dx. Now, it looks like this could be symmetrical about the y-axis, this formula here. So let's check that out. So 8, let's just put in the original formula first. 8 cosine of x minus secant x squared. All right, now let's take this and put in minus x. Those are the same. So f of x is equal to, or f of minus x is equal to f of x. So this is an even function. And I checked that because we were going from minus pi over 3 to pi over 3, like minus a to a. That's when you want to check if your function is symmetrical, if you're going from minus a to a. If you have an even or an odd function and then you're going from like the same point in the minus direction to the positive direction, then you can simplify the definite integral. So what we can do is we can, since this is an even function, if this was an odd function, this would be equal to 0. We're done. But since this is an odd function, what we can do is go from 0 to pi over 3 and bring out a 2. And then like that. So it'll make it a little bit easier to evaluate. So, all right, 8 sine of x minus tangent of x. That's the antiderivative. Right? Take this derivative. You get 8 cosine of x minus secant squared of x. So this is 8 times sine of pi over 3 minus tangent pi over 3, okay, minus 8 sine of 0, so 0, and then tangent of 0, I believe, is 0. Tangent is equal to sine over cosine, yeah. So, all right, that's it. So 8 times sine of pi over 3 minus tangent pi over 3. 3 root, oh, well, then times 2. 6 root 3. And that is this area. All right, we'll work the rest of these problems in the next video.